Hi students, in this first video for chapter 7, we are now going to talk about our molecular geometries. These are the shapes that our molecules are now going to adopt. These are all based on what we call the valence shell electron pair repulsion, or VSEPR theory. The VSEPR theory predicts the geometry of a molecule from the electrostatic repulsions between electrons. We are going to look at the bonding and non-bonding pairs and how this affects our geometry. The simplest way of looking at this is that we want to get electrons as far away from each other as we can. So what we're going to do for each one of these examples throughout this video is give it a class. That class is going to be based on the number of bonded atoms, the number of lone pairs. Then we are going to assign what is called an electron pair arrangement or electron pair geometry. There are going to be 5 of these throughout the entirety of this video and the next. This is going to be based solely on the electrons. The molecular geometry may match up to that electron pair, or as we see in the next video, once we add lone pairs to the central atoms, you are going to get different molecular geometries. So the first group that we are going to talk about is what we call the AB2 group. This is going to have 2 bonded atoms to our central atom. For this video, we are going to have no lone pairs. Lone pairs actually affect our molecular geometries, and they will be handled in our next video. So the farthest that we can get 2 bonding pairs of electrons away from each other is 180 degrees. This is going to give us the linear electron pair arrangement. Notice that the 2 bonding pairs are as far away from each other as they physically can. This is going to give us the linear molecular geometry. So when we have 2 attachments and no lone pairs, we are now going to see the linear electron pair arrangement and linear molecular geometry. You can see this here with beryllium chloride. Notice that we have 1 bonding pair and 2 bonding pairs. We have no lone pairs. So this means that those electrons want to be as far away from each other as possible, and that is how we get the linear molecular geometry. The other part about this is notice that the lone pairs on the chlorine do not affect our central atom. The central atom is the one that dictates the molecular geometry. If there are multiple central atoms, this means that different parts of different molecules could have different molecular geometries. So if we get to a point in which we have multiple central atoms, you must assign multiple molecular geometries. But the lone pairs on the chlorine do not affect the beryllium in this case. So now let us go and look at what we call the AB3 group. The B3 means that we have 3 bonded atoms. Once again, we have no lone pairs, but now we are going to add an attachment in which we are going to now have to change that angle of the 180 degrees. Well, just imagine taking a circle at 360 degrees and evenly cutting it up into 3 parts. When we do that, you are now going to get what is known as the trigonal planar electron pair arrangement, and you will result in the what we call trigonal planar molecular geometry. Notice that the bond angle from terminal atom to central atom to another terminal atom is 120 degrees. A way of noting this and a way of seeing this can be done with this figure here. So if you see how this rotates, notice that you are going to see a circle split up into 3 even chunks with those atoms being 120 degrees away. This is adopted from our boron trifluoride. So remember when we were drawing our Lewis structures, we would have our fluorine attached to our boron, attached to another fluorine, and another fluorine down. If we were to put in our lone pair, you will see that my boron does not have a lone pair attached to it. We have 3 equal attachments, but now the 90-degree angle does not look as correct as we are hoping. So a much better representation is going to be that matching the figure you see above. And that is taking and representing our angles much cleaner and trying to represent our bond angles correctly in our new drawings. So this is now where you are going to learn Lewis structure drawing 202. 101 was make everything 90 degrees. Now what we want to do is try and make our Lewis structures look fairly similar to the actual molecular geometries. Now that we've done 3 attachments, let us go and do a 4th attachment. The 4th attachment can start to make things very complex because, as you would think, you would say, oh, I have a circle. 360 degrees divided by 4 gives us 90 degrees. Well, that is not the case because we are going to go into a 3-dimensional geometry, that of a tetrahedron. A tetrahedron has 4 vertices. So we are going to look at those vertices, and the bond angle for those vertices is going to be 109.5. This gives us the tetrahedral molecular geometry. So what does that look like? Well, as you can see here, we have our tetrahedron for methane. Methane is going to be a carbon bound to 4 hydrogens. So because I have 4 equally bound attachments, my Lewis structure like this isn't very representative of what that molecule actually looks like in its true representation. So now what can we do to make it look like the figure that I see there? Well, a better representation of our drawing is going to be using what we call the wedge dash notation. What we are going to do is take 3 of our atoms and leave them in the plane of our paper. You can see those here. But now notice for this attached atom here, it's really coming out at us. How do I signify that? Well, this is using what we call the wedge notation. The wedge notation is saying that it is 3-dimensionally coming out at us. Look at how that is done. The dash notation is there to represent atoms that are going away. Notice that this one is going back away from us. How I can represent that is doing an ascending dashed line and then putting my atom at the end. So now you can see between my 2 examples, while my Lewis structure for my methane originally had 90-degree bond angles, we can now see that this very much gives us the ability of a 3-dimensional structure in which we can predict the bond angles of 109.5 degrees. You are going to see this molecular geometry all the time, especially when dealing with carbon. The reason why is that carbon likes to have its octet with 4 bound pairs, and you can see how that we result to that. So now that we've done 4 attachments, these are going to be molecular geometries that you see all the time. But what happens if we go and have our expanded octet? Well, what we can do is now go to the AB5 group. This is the first of the expanded valence in which we can have more than 4 attachments. So now what we have is 5 attachments. We have no lone pairs still. And what happens in this case is that we are going to really get 2 very distinct zones. A zone located here around the middle and 2 attachments at the top and bottom. What this looks like, if you were to cut this in half, is a trigonal pyramid. But then it's reflected upon itself, so this is known as the trigonal bipyramidal. This is going to look like a trigonal pyramid reflected upon itself. This one can be a little hard to see from time to time, but one of the things that you're about to notice is that there are 2 different bond angles that we need to associate. A very good example of this is phosphorus pentachloride. So now you can see here that we are rotating this molecule, but as you're seeing through here, there really looks like that 3 of the attachments are the same, while 2 of them are slightly different. So the best way of looking at the trigonal bipyramidal electron pair arrangement is that it's really trigonal planar with 2 vertical attachments. So let's go ahead and look at our trigonal planar species. You see that group right through here in the middle. Notice that that is very similar to our trigonal planar that we saw before. But now we are going to have our top attachment here and our bottom one here. So how do we draw this? Well, when it comes to this, we want to take our chlorines, especially our vertical ones, and put them in the plane of our paper. So there we have our top and bottom chlorine attachments, plus we now have a chlorine coming straight out and to the right. What can we do for the two attachments, one coming out at us and one going away? Well, this is another use of our wedge dash notation. So if I go in and draw the chlorine that is coming at us and to the left, and then you can also then see the one that is going back here and to the left. This helps show what we need to show. Notice the two different bond angles. If we are going from a top position to one of our horizontal positions, this is a 90-degree angle. However, if we are going between our middle positions, we have a 120-degree bond angle, very similar to that of our trigonal planar. Because we have two different bond angles, we are going to have to signify these as two different attachment groups. The groups that I have circled, located on the original figure, are located around the equator of the molecule. Just imagine the equator on a globe. We are going to call these equatorial attachments. These are attachments that are located right along the middle of our atom. So then we need to go and signify our top and bottom attachment because they interact with the other atoms by a different bond angle. These are along an axis of rotation, so we are now going to call those axial. So the top and bottom are going to be what is known as axial attachments. So we are going to have axial attachments at the top and the bottom, while we have three equatorial attachments, all being separated by 120 degrees. The axial to equatorial attachments have a 90-degree bond. So now we are going to go to our last molecular geometry. The last one we are going to discuss is the 6 attachment. This means that we are going to have 6 attachments located around our central atom. There are no lone pairs. And finally, we are going to call this the octahedral. Now, many students get this confused in a lot of ways because octahedral meaning 8, that doesn't make sense when using 6. But when you have 6 attachments, you are actually going to form a 8-sided figure, that of the octahedron. This is going to look like a square pyramid that is going to be reflected upon itself. So now we can go ahead and look at what it looks like in real life. Now, one of the issues that comes up with the octahedral electron pair arrangement is that you're going to want to immediately assign octahedral positions very much like the trigonal bipyramidal using axial and equatorial. However, notice that we have the same bond angle for all of these positions. So as we have this drawing, you are probably looking going, these 4 here located around the middle very much look like the equatorial positions in our last figure because they're around the middle, meaning that the top and bottom would be axial. But now let's take a look at the video that you see here. As you can see, we have a very nice look of 4 what you think would be equatorial fluorines located right around the middle. But once I start the video, you are going to see that all of a sudden, all of these bonds are equivalent. So what you think was axial or equatorial can easily be interchanged with another position. So we are not going to use the axial and equatorial nomenclature when doing this process. So the question becomes, how do we draw this? Well, there are 2 ways to draw our sulfur hexafluoride. The first is going and doing and putting as many species into the plane as possible. So if we were to do that, we would have a fluorine attached to a sulfur, and then to a bottom fluorine, and then putting 2 more fluorines in the plane of the paper. Then what I need to do is go and put one coming out at us, as you see here, and one going away, which you see here back on the left. So if it's coming out at us, we are going to use the wedge notation that we have with a fluorine, and then we would end up using the dash notation over on the other side. While this figure is very nice and very simple to draw, it has a hard time of really retaining that all of these have the same 90-degree bond angle. You can see the 90 degrees here, but then it looks like 45 degrees here and it looks a little crowded. So there's another way of doing it. As you become more comfortable with your drawings, you are more than welcome to go and use a different theory, and that is using more of the wedge dash notation. That means that we would have 2 wedges coming out, one to our left and one to our right that you see here, and then going back as you see here, and then we have one going back to our left here. Both of these drawings are completely acceptable and fine, and you just want to use the one that gives you the most knowledge to help you in your process as you're going along. But remember, for the octahedral electron pair arrangement, we do not have equatorial and axial. All of these positions are equivalent because we have a 90-degree bond angle for all of our atoms. So here's a really nice summary of the 5 molecular geometries that we've discussed in this video. These are the ones in which the central atoms have no lone pairs. There are 5 possible answers: linear, trigonal planar, tetrahedral, trigonal bipyramidal, and the octahedral. You are required to know not only the names, not only the electron pair arrangements, but you are also expected to know the various bond angles of the examples and any of our species that we find. So let's go ahead and try this first example for Chapter 7. Glyphosate is a common herbicide that is safe for animals while being toxic to plants. Using the figure to the right, what is the O double bond carbon single bond oxygen bond angle in our glyphosate? Notice that we have that attachment right here. So the question that is going to become is that we need the molecular geometry of this carbon right here. So let's look at that carbon. How many attachments does that carbon have? Well, it is going to have 3. Let us go in and circle this carbon here. We have the doubly bound oxygen. Double bonds and triple bonds only count as one attachment in the VSEPR theory. We are going to deal with them a little bit different later, but in this case, that carbon has only 3 attachments, those 3 attachments being different. We have a carbon, we have a singly bound oxygen with 2 lone pairs, and then finally here we have a doubly bound oxygen with 2 lone pairs. But for our central carbon is the only thing we are worried about. So now we have 3 attachments. 3 attachments means what molecular geometry? This is going to be the trigonal planar molecular geometry. So now, what is the bond angle for the trigonal planar molecular geometry? Well, this is having 3 attachments. This is going to be 120 degrees. So now, as you can see and look at very complex molecules, you are going to be able to decipher not only the shape, the electron interaction, but also the bond angle. And this is going to help you not only in this course, but is going to help you in such courses as organic chemistry and even into biochemistry. In our next video, we are going to complicate the situation by adding in lone pairs on our central atom and showing you what it does to our molecular geometries. Have a great day.